Okay, good morning everyone. Thank you for the introduction. So I've checked and this is already the fourth time I'm speaking at BruCON, so it's great to be here again. I hope you'll enjoy the talk. So today I'm going to present some work we did on WPA3, and I did this together with Eyal Ronen, but today I'm here to present it. So let's start first with a quick introduction. I'm talking here about the Dragonfly handshake of WPA3. Well, actually, before I get into the details, I have one other thing to mention. And this is that this work was also presented at Black Hat, where it was nice enough that we won a Pony Award for the work that we did here for the best cryptographic attack. And I think there are two main reasons why we were lucky enough to get this award. The first is because in this work we cover various attacks against cryptographic protocols. So it's also a good overview to know what all the possible things that can go wrong when you implement a crypto protocol are. And the second thing is that this research also has an interesting story, because the designers of WPA3, they were actually warned about some weaknesses, but somehow it made it into the WPA3 specification anyway. I think those are two reasons that contributed to this nice award. But let's get back to our story here. I wanted to introduce the Dragonfly handshake of WPA3. And the Dragonfly handshake is a handshake that already existed for a while, in fact, because it's also used in the EPWD protocol. Now, what is the EPWD protocol? Well, this is a protocol that is also used in enterprise Wi-Fi networks to authenticate users. For example, in about, I would say, 5% of Ethereum networks and a small percentage of also maybe company networks where you have to log in using a username and a password, and about 5% of those, the EPWD protocol is used. And this Dragonfly handshake that is used internally in both EWD and WPA3, we call it a PAKE, a password authenticated key exchange. Now, what does that mean? Well, what that means is that this handshake provides mutual authentication. The client has to prove that it knows the password, and the access point also has to prove that it knows the password. In other words, with this handshake, you're also sure that you're not connecting to a rogue network. At the same time, this handshake also negotiates a fresh session key, and this session key will be used after the handshake to secure your normal data traffic. And the most important property of the Dragonfly handshake is that it also prevents forward secrecy and that it defends against dictionary attacks. What does that mean? Well, as you may already know, with WPA2, an attacker can simply passively monitor or sniff the handshake, and he can then take that handshake offline and perform dictionary and brute force attacks against this captured handshake on a laptop or on GPUs and very efficiently try to crack the password. But with WPA3, that is no longer possible. If you passively capture a WPA3 handshake, you cannot take that handshake offline and then try to do dictionary or brute force attacks against it. And forward secrecy means that if you capture some network traffic now, and a year later I learn the password of the network, I cannot go back in time and decrypt the traffic I captured a year ago. While with WPA3 that is possible. With WPA3 I can collect someone's network traffic, and if I then later on learn the password, I can go back in time and decrypt the traffic. But with WPA3 that's not possible. So those are two very interesting properties, and they make WPA3 a much better choice and actually just a modern crypto protocol. And one last thing I want to mention here is that certain other PAKEs, they also provide one fourth property, and that is that they protect against a so-called server compromise. So what I mean with this is that some PAKEs, but Dragonfly doesn't have that property. They provide a defense if your access point or if your server is compromised. Basically, the way you have to imagine this is that with some PAKEs, you can store the password in a salted version. But with WPA3, that is not the case. With WPA3, both the access point, the router, and the client, they need to store a plain text version of the password, which means if your router or a client is compromised, the adversary will learn the plain text password. So that's a very quick introduction about the properties of WPA3. I will now very briefly explain how this handshake works in practice. And let's say that we have a client here that wants to connect to the access point. And they are using WPA3. The first thing that both these devices need to do is they need to convert the plain text password, which is, for example, just an ASCII or in Unicode. They need to transform this to a so-called group element P. Now, what is this group element P? I will go into it in a bit more detail later on, but basically it's sort of a mathematical presentation of the password which we will be able to use in the actual cryptographic protocols on the cryptographic calculations. Because, you know, an ASCII password isn't really a valid number. You have to convert it somehow into a mathematical object, so to speak. And this is the first thing that both devices need to do. They need to convert the password in something that can be used in our cryptographic calculations. And once that is done, they can execute the actual handshake. And this handshake consists of two main phases. The first phase is called the commit phase. And to simplify it a bit here, the commit phase essentially negotiates a shared key between both the client and the access point. And the second phase is called the confirm phase. And in this phase, both devices confirm that they negotiated the same session key, which in turn also means that they use the same password. So if the confirm phase succeeds, then both parties know of each other that the other one indeed has the correct password and is allowed to connect. Now, the important thing about the Dragonfly handshake, and where actually most of the things will go wrong and that we will discuss, is in how this password is converted into a group element. And I will now explain in a bit more detail how this password is converted to this element P. But before I do this, I have one more important remark. And this is that the Dragonfly handshake can be executed using two different so-called cryptographic groups. The first is called mod P groups, and the second is called elliptic curves. And I will briefly introduce both, and I will explain for both variants how this algorithm works that converts the password into a group element P. So the first case is here, as you can see, the mod P groups. Now, I don't expect any of you to know what mod P groups are, so let me give you a very quick introduction, and don't worry, we're not going to use a lot of math here, it's going to be quite simple. So, what is a mod P group? Well, we can treat this in very simple terms. Basically, it means that we are working on numbers, so all our crypto operations are done on numbers, and all these numbers are smaller than a certain prime. And that's the only thing you need to remember. One other thing is that the numbers we are working on here, they need to satisfy a certain equation, but understanding that equation won't be too important. And for those of you that are wondering, the Q here represents the amount of elements in the group, but again, that's not too important to understand the talk. Just remember that all the numbers we are operating on, they have to be smaller than the prime P that we are using here. In other words, all operations are done modulo the prime. And that's also why it's called mod P groups, because it's modulo P. Okay, so that's a very quick introduction to mod P groups. So now the question is, how can we convert a plain text password into a number that has these properties? Well, a naive way to do it is the following way. Here, we take the plain text password and we hash it together with the MAC address of the client and the access point. And the result of this hash input, we interpret it as a value, as an integer. Now there is one more thing that we need to do. We need to make sure that this integer here, that it satisfies this special equation. And without going into too much detail, to make sure that this is the case, we can simply perform this calculation. And then we are sure that the value p here is indeed a member of this mod p group. So you don't need to know why this works, just accept that this works. If I execute this, p is a valid member of the group, and then we are done. Now, this seems to work, but there is actually one small problem. And it turns out this is going to be a major problem. The problem is that for certain mod p groups, there's a high chance that this value here, the output of the hash, will be bigger than the prime of the mod p group. And again, I'm doing a high-level explanation here, but if this value is bigger than the prime of the group, then this formula would not be 100% correct, because then there are some biases and maybe the adversary can abuse this. So essentially, we have to make sure that this output here, this value, it has to be smaller than the prime of the group. And especially for mod p groups, for specific mod p groups, this has a high probability of happening. Now, fortunately, the designers realized this, and they decided to fix this. And what was their solution? Well, they simply decided to put an if test here, and they're going to check if this value is bigger or equal than the prime, then we need to do something. And what did they decide to do? Well, they decided to include a counter in this algorithm. So the counter starts at 1, it's included in the hash function, and if we then get a value that is bigger than p or equal to p, we simply execute a new loop, meaning we increase the counter. Since the counter here is included in the hash, this will result in a new output for the value, and hopefully on the second try, value is smaller than p, and we can continue the algorithm. And it can be that we need multiple iterations here in this algorithm. Now also, as a quick remark, if you have questions during the talk, you feel also free to raise your hand and ask them. It's always nice to have some interaction as well. Now, my question here is now, what is wrong with this algorithm? Based on this description, you can already see what will go wrong. And the problem here is that if we look here at the password, we can see that the password will influence how many iterations are needed to convert the password into this group element P. For example, for password A, I might immediately get a value that is smaller than P, and I might immediately find the group element here. But for a different password, for password B, I maybe need multiple iterations here in this for loop. And this means that the execution time of this algorithm depends on the password being used. And this is a bad thing because this is essentially a timing side channel, and we will be able to abuse this leaked information to then brute force the password. And this is a bit surprising that there are no countermeasures against this timing leak, because the designers of this algorithm, they were actually warned by this issue by both the IETF and the CFRG. Now, I assume maybe some of you know already what the IETF is, but basically the CFRG, it's you can just consider it an online mailing list where people can propose an algorithm to cryptographers, and they will then perform some sanity checks, and they will try to break the algorithm, so to speak. And on both these mailing lists, some researchers actually found some flaws, and they warned the designers. In fact, this was already back in 2010 when this handshake was proposed. Already then, some people said, you know, this algorithm is not a good idea because it's likely vulnerable to timing attacks. And unfortunately, this comment was dismissed Because the reaction was basically, well, we're not really sure how important this timing leak is. Yeah, there might be this timing leak, but I don't think it will leak the actual password, so they didn't think it was serious, and they thought it wouldn't be a trivial attack. So they essentially ignored this comment. And it turns out that this is going to be a major flaw in the algorithm. Now, let's come back to this remark here, where initially they thought it wouldn't leak the password. So how can this timing leak the password that you are using? Well, let me explain this with an example. Let's say that we have an access point that is running somewhere, and we are able to initiate a WPA3 handshake with it, at least the first phase of the handshake, because we don't know the password yet, so we cannot complete the handshake. But we can initiate the handshake with the access point, and let's assume that we are able to measure how many iterations this access point needs to convert the password into this group element P. So to repeat that, we have an access point, and we're going to measure how many iterations of this algorithm the access point needs. And in the first step of the attack, we're going to connect with a client that has MAC address A. So our own laptop is using MAC address A, and we perform a timing attack to learn how many iterations the access point needed. And in my example here, the access point needed 2 iterations to convert the password into this element P. What I can do now is I can take a dictionary of passwords. Here in my example, I'm just going to use 3 passwords. And I can then run this algorithm offline on my own computer with this password. So I can take here, I can guess a password, I can compute the algorithm that I just showed myself, and I can then determine how many iterations would be needed if indeed we are using this password. And in my example here, if the access point, if the network would have been using password 1, then this algorithm would have needed 1 iteration in the algorithm. And this doesn't match our observation because we measured the actual access point that it uses 2 iterations. This means here that password 1 cannot possibly be used by the network because if it was used, the access point would also execute 1 iteration, but that's not the case. Now, as you can see here, password 2 and 3 are still possible because if we simulate the algorithm offline, we notice that they both also need 2 iterations to convert the password. And this matches what we observed from the access point. So both these passwords are still possible. So now the question is, how can we further reduce the amount of possible passwords? Well, the interesting thing is if we go back to the algorithm here, we can see that the MAC addresses of the client on the access point, they will also influence this algorithm. Because if you use a different client MAC address, the output of this hash function will be different, and this means you again get a different amount of iterations that are needed. So that's the core idea here. The core idea is that we can spoof a different client MAC address, and then we can again measure how many iterations the access point will need in our algorithm. So if we go back to our example here, what an adversary can do after this first step is that he or she can now spoof a different MAC address. Then we can again do a timing attack to measure how many iterations the access point needs. And in this case, the access point needs, for example, 1 iteration. We can then take our remaining possible passwords, simulate this algorithm offline, and here we see that password 2 would need 2 iterations. That doesn't match our observation here, meaning we can again exclude the password. And we can continue doing this with multiple MAC addresses until we uniquely determined the password being used by the access point. Now, to give you an idea how many MAC addresses we need to spoof in this way, if we would take the ROCU database as a reference, and if we want to try to uniquely determine the password in the ROCU database, assuming this password is in this database, then I would need to spoof on average 17 MAC addresses, which is not too much. And the intuition behind this here is that for every MAC address, we can eliminate, say, roughly half of all the passwords in the database. Now, in case this was a bit fake, the main takeaway message here is that by measuring how many iterations that the access point needed to convert the password, this information essentially forms a signature of the password. So that's the one thing I want you to remember here. The amount of iterations that the access point needed, it forms a signature of the password, and this signature can then be used to brute force the password offline. Okay, so we now almost completely covered this initial attack. There is one thing I didn't explain yet, and that is whether it is actually feasible in practice to measure how many iterations that the access point needs. So we decided to test this out in real life, and what we did is we took a Raspberry Pi 1B. And the reason we took this Raspberry Pi 1B is because its CPU matches the CPU of common home routers and also the CPU of some professional access point. Because generally your home router doesn't have the most performant CPU, and we found that the Raspberry Pi was a fairly decent match. When we did this work, there were few professional access points available, so that's also another reason why we used the Raspberry Pi. But for the software that we ran on our Raspberry Pi, we used HostAP, which is an open source implementation of an access point, and it is in fact heavily used in Linux on Android, and practically every home router will be running HostAP. And even some professional routers, they also use HostAP. So with this setup, with our HostAP running on a Raspberry Pi 1, we performed our timing attack, and based on this graph, we can see that if the access point here needs only one iteration, it clearly has a different response time than if the access point would need 2 iterations. So here, this orange line is if the access point needs 2 iterations. We can see here that this indeed is measurable. And to give more concrete number here, if I want to determine against this specific setup how many iterations that the access point executed, then I need to perform around 75 timing measurements. So as an adversary, I need to initiate 75 incomplete WPA3 handshakes, and after doing this, I learn with a high probability how many iterations were needed. In other words, this timing attack is definitely feasible in practice, especially against devices with a weaker CPU. And maybe one other remark here is that I executed this attack in my own apartment, so there was some background noise. So I wouldn't say this was in the worst situation, but we also didn't do this in an optimal case. It's just on an average day environment that we performed this attack. So good, we already covered quite a bit now. This is the timing attack that we discovered, and it's, I would say, one of the main issues that we found, namely these timing leaks. But there's actually a second part to the story as well, because remember that I said that the Dragonfly handshake can be executed using either mod P groups, but it can also be executed using elliptic curves. So now the question is, if we use elliptic curves, do we also have a timing leak? Or are we secure in that case? Now, to understand this and to answer this question, let me give a 1-minute introduction to elliptic curves. Essentially, if we use elliptic curves, all operations are performed here on a point x and y, and again, both the x and y coordinate need to be smaller than the prime that is being used. And the second condition is that x and y need to satisfy this equation here. And again, that's all we need to know. We're not going to use any more math other than this. The question now is, how can we again convert the plain text ASCII password, in this case, into a point XY here on the elliptic curve? And the way that this is done for WPA3 is very similar to the mod P case, because we again have an algorithm here that here it takes the password, it hashes it together with a counter on the MAC address of the client on the access point. But in this case, the output of the hash function is treated as the x coordinate of our point that we want. And then the idea is we take this x coordinate and we can see, and then we check if there is a corresponding y value as well. On this y value, we would have to calculate it here using the square root. And to give a simplified explanation here, there won't be a corresponding y value for every x coordinate. And the intuition here is that we have a square root, and if we take the square root of a negative number, that doesn't exist. And the same situation, at least intuitively, implies here as well. This square root doesn't always have a solution. So that's why if we have this x value, we first need to check, does this square root actually have a solution? And if it does, then we know that we found a point x and y that indeed lies on the elliptic curve and that we can use. So I hope that's a bit clear. And what's the interesting thing here is that remember that the Dragonfly handshake is used both by WPA3 but also by EAP-PW. And it turns out that in the EAP-PW protocol, PWD protocol, which we call, it is used in Wi-Fi networks where you have to log in using a username and a password, then exactly this algorithm is being used to convert the password into a elliptic curve, into a point on the elliptic curve. And this is problematic because here we have exactly the same vulnerability as before. The password here influences the number of iterations that this algorithm executes. So again, we have a very basic timing leak here, and the EAP-PWD protocol is exploitable in exactly the same way as we saw before. So that's bad for EAP-PW. For WPA3, the situation is a bit more interesting, because in this case the designers actually realized that this timing leak exists, and when using elliptic curves they actually have a countermeasure against it. What they do here in WPA3 is they always execute 40 loops of the iterations, and for the element P they simply pick the first solution here that we find. So if we find a solution in the first iteration, we assign the result to P, and then we execute 39 additional iterations so that this algorithm always executes 40 loops. And then the idea is that there won't be a timing leak because the algorithm always executes in a constant amount of time. And this number 40 here was chosen such that the probability of needing more than 40 iterations is extremely low, that it normally shouldn't occur in practice. On at first sight, this actually looks like a solution that will indeed defend against these timing leaks. However, there is one problem. And the problem is that if we use a certain type of elliptic curves, because when you're using elliptic curves, you have multiple choices of the curves you want to use. For example, you can use NIST elliptic curves, in which case this would be quite safe to use. But WPA3 also supports so-called brain pool curves. And it turns out, when we use brain pool curves, we have a similar problem as before. Namely, this output value here, and the output of the hash function, which will be equal to x, it has a high chance of being higher than the prime of the elliptic curve. And again, this would cause issues in the remaining calculations because it might introduce a bias. But the thing to remember here is we want this x value to be smaller than p to avoid any possible issues. So they had to implement a defense against this. They had to somehow handle the case that X is bigger or equal than P. And how did they solve this? Well, they simply added an if condition here. So what they did is, if X is bigger or equal than P, then we just execute another iteration. So does anyone have any idea what is wrong here with this algorithm now? Yes, you again get a different execution time, because this amount of code here is then skipped. And even more problematic, the amount of times that this code is skipped will depend on the password. So again, we have a timing leak here. Now, I'm simplifying here the high-level explanation of the algorithm a bit. In practice, there are some additional technicalities that we have to handle when we want to exploit this. But essentially, we have the same vulnerability and also the same exploit mechanism as before. We can measure the execution time of the access point or even of the client. We can measure how many times this block of code was skipped. And again, this forms a signature of the password. Now, this is simplified a little bit, but the high-level idea is the same. That's again what I want you to remember here. The execution time, so the amount of iterations that are needed, in this case, the amount of times that this block was skipped, it will again form a signature of the password. On this signature, we can take offline to then perform dictionary or brute force attacks. Okay, good. So we now covered all the possible timing leaks against this algorithm. And in my opinion, these are really design flaws in WPA3. Technically, you could implement this algorithm to avoid all these timing leaks, but as an ordinary programmer, or even as a good programmer, if you are not aware of all these possible issues, then it's very hard to implement this in a secure way. And even for crypto experts, this can be tricky to implement in a constant time way because it's very easy to screw up, basically. So yeah, in my opinion, this is a design flaw. So we now covered timing leaks. The second thing I briefly want to mention is that it's also possible to perform cache attacks. So let me again go back to our algorithm here. Essentially, what I as an attacker want to know in order to break this algorithm, I want to know in which iteration a solution was found. Because if we would know exactly in which iteration a solution was found, then we again have information about the password, and we can again use this leaked information in an offline brute force attack. And what we can do here is we can use flush and reload to detect when this piece of code is being executed. Now, you don't need to know the details of how flush and reload works. Just assume that as an adversary, we can determine whether this piece of code is executed, and we want to know in which iteration it is executed. There's one problem though, and this is that this code will always be executed at some point. It can be an iteration 1, it can be an iteration 10, it can be an iteration 30. So we don't just need to know that this code is executed, we also need to know in which iteration it was executed. And now the question is, how can we determine, using flush and reload, to determine in which iteration it is executed? Well, our solution here is to also use flush and reload to monitor how many times the hash function here is executed as well. And essentially, we use that as a timer to know in which iteration we are. For example, using flush and reload, we can determine the first time that this hash function was executed, and we can also detect the second time that this hash function was executed. And we can then check whether between the first and second execution, if this code was executed as well. And to summarize, this will allow us to determine whether a solution was found in the first iteration or not. Now again, the main takeaway message here is that by using these attacks, we again learn a signature of the password. We again know some leaked information, and we can use this in an offline dictionary or brute force attack. What I do want to mention about this attack here is that it requires a quite powerful adversary, because in order to perform these cache attacks, you need to be able to run unprivileged code on the victim machine, on the machine of the victim. Now, in the case of smartphones, this might be possible by making the victim install some kind of application. The application doesn't need special permission, so this can be possible in practice. And if you use an old browser, an adversary can even perform these attacks from JavaScript if some other conditions are met as well. The second condition is that the attacker also has to be within range of the victim in order to either set up a malicious client or access point. Now, as you can see here, these are more strict conditions, so in practice it's unlikely that someone will exploit this, but for a modern crypto algorithm, it has to be able to defend against this. This is not acceptable for a modern crypto protocol to be vulnerable to this type of attack. And here again, we can abuse this leaked information, as I mentioned, to try to determine the password. And here we use the same technique that we spoof multiple MAC addresses to get enough information to then uniquely determine the password. One thing I also want to discuss here is that I've always been talking about performing these dictionaries on these brute force attacks, but I haven't yet explained how costly those attacks are. The reason why I waited with explaining that is that we can use exactly the same brute force algorithm both for our timing attacks and for our cache attacks. So that's nice. We can implement our brute force algorithm once, and we can use it in both the cases that I just discussed now. And what we did is we tried to optimize and estimate the cost of a brute force attacks using GPUs. And here we found that we can go through a dictionary of 10 to the power 10 passwords for less than $1 on Amazon EC2 instances. Now, what does this number mean here, 10 to the power 10? Well, this number is bigger than any password dump you can find online. It's bigger than the RockU password dump. It's bigger than all the passwords on Have I Been Pwned. It's also bigger than nearly all English dictionaries that we found, which means that if you take all the password dumps you can find, if you add all the English dictionaries to it, it will be smaller than this number, and you'll be able to go through that dictionary for less than $1. So this is quite efficient. And inspired by this, we also decided to calculate how much it would cost to perform a full brute force attack of all possible 8-character passwords. And in this case, we assumed that every character can have all 256 possibilities, so we're really checking every possible password of length 8. And then we found that if we attack mod P or brain pool groups, brute forcing this costs less than $70, which it's a bit of a bigger price, but still fairly doable. If we attack NIST curves, then in this case the cost is much higher. It would be $14,000. Now, on one hand, this is a big amount. On the other hand, the fact that we can attack a modern crypto algorithm for only this small amount is again unacceptable. And in fact, in the meantime, we found some other ideas to optimize this, so likely we can make this number much lower in practice. But this shows that these dictionary attacks and these brute force attacks, at least computationally, they would be feasible to do in practice as well. So we now covered the timing attacks. We have our cache attacks. We can do our dictionary attacks. You'd think by now we covered most of the vulnerabilities, but we're not done quite yet. One thing we also did is we looked at implementations of Dragonfly. So on one hand, we looked at some early WPA3 implementations, but we also looked at EAP PWD implementations. The reason why is that Remember, as I said in the beginning, the Dragonfly handshake is also used in the EPWD protocol, and it has been around much longer, so there are more implementations of it. And the first attack that we checked for is a so-called invalid curve attack. Now, what happens in this attack? Well, if we are using elliptic curves, and we are using the Dragonfly handshake, then the first message that the client sends, it will include a point X and Y on the curve. This is simply part of the protocol. And a legitimate client always sends a point X and Y that is on the curve, that satisfies that special equation. But if we are an adversary, we don't need to do that. We can just send a point that isn't on the curve. And normally a proper client or a proper access point is supposed to check this. It's supposed to check whether the received point X and Y is on the curve or not. And if it's not on the curve, it's supposed to just ignore the message. But we found several implementations that don't perform this check. They don't check whether X and Y is on the curve. And as an adversary, we can very carefully select the values for X and Y here, so that the negotiated session key only has a very small set of possible values. So again, by very carefully selecting the values for X and Y, assuming that the access point is vulnerable, there are only, say, about 3 possible values of the key that is being negotiated. And a vulnerable access point won't realize this. It will simply reply using a commit. And then we, as an adversary, we can guess the key that the access point calculated here. And we have about more than 60% chance of guessing this correctly. And then we can just continue the handshake as usual. And if we successfully guessed the key, which again, there's more than 60% of guessing it correctly, then we effectively completely bypassed authentication. Meaning we can log in under any username, and or with WPA3 we can just access the network without knowing the password. Now, the most surprising thing here is that we looked at several EPWD implementations, and all of them were vulnerable to this attack, which was very surprising. The only bright side, I would say, is that if you have an EPWD implementation which uses a newer version of OpenSSL, then OpenSSL already contains a defensive check against this, and then the implementation won't be vulnerable. But if you, for example, use FreeRadius or Radiator with an older but still maintained version of OpenSSL, then you can simply bypass authentication and you can log in as anyone that you want. With WPA3, the situation was a bit better. There we only found one implementation that was vulnerable to a variant of this attack. So that covers the first implementation-specific issue. We also found another issue, and this is that one implementation in particular, namely the EPW implementation of Aruba, it uses predictable random numbers. And whenever your random numbers are predictable, you have a problem. And in the case of WPA3, this problem is actually quite bad, because if with WPA3 you use a bad source of randomness, you can in fact recover here the password element P, and with that information you can just connect to any network. You can just connect to the network. You basically know the password of the network. And this situation is in fact worse than WPA2, because if you use a bad source of randomness with WPA2, the impact is fairly minor. While with WPA3, if the implementation uses predictable random numbers, all bets are off, because you can recover P, and then you can, as an adversary, connect with the network. And I think this can be quite risky in practice, because I can imagine certain IoT devices, or at least devices that are very resource constrained and don't really have a proper source of randomness. I expect that in the future some of them might be vulnerable to this. They might use a bad source of randomness, and then you can basically break WPA3. Another implementation bug that I want to discuss is specific to free radius. And what free radius does is that in this algorithm that converts the plaintext password into this group element P, remember that we need a variable amount of iterations. Strangely enough, free radius aborts the handshake if more than 10 iterations are needed. And we as an adversary can easily detect this because in this case free radius just sends a failure message, so we can detect when free radius needed more than 10 iterations. And in practice, about 1 in every 2,000 handshakes, or at least connection attempts, indeed need more than 10 iterations. So as an adversary, what I can do now is I can try to initiate 2,000 connection attempts to the free radius server. On average, one of those connections will fail. And on the connection that failed, I then know that free radius needed more than 10 iterations. And this information again forms a signature of the password, and we can use that signature to brute force the password. So the lesson here is that aborting this algorithm if you need higher than a certain amount of iterations, that's bad. You should not do that, because then you again leak information. A similar problem is also present in the implementation of Aruba. It aborts when you need more than 30 iterations, but this is very hard to exploit in practice because you really need to send an absurd amount of connection attempts in order to ever cause Aruba to abort the connection. Because needing more than 10 iterations has a very low probability in practice. Okay, so those are all the implementation issues. We aren't done yet. I still have one more thing, one more set of attacks to discuss. On those attacks, they're all more specific to the Wi-Fi area. In particular, let's go back here to the initial scheme of our handshake. Remember, you should definitely know that by now, in the beginning we have to convert our password to this group element P. And one downside is that the access point cannot cache the resulting group element P here. It cannot calculate this once and then later on keep reusing this for subsequent connections. It always needs to calculate this from scratch whenever a client connects. And the reason why is that this element P here also depends on the MAC address of the client. And of course, we cannot predict, at least in general, the MAC addresses of our clients. Which means whenever a client will connect, an access point needs to execute this algorithm. And this algorithm is quite computationally intensive. Because remember, for when we use elliptic curves, we always use at least 40 iterations. And what we tested here is we took a professional access point that already supports WPA3. We configured it to use the most secure and also the most biggest elliptic curve. And in that case, we found out that if we initiate 8 connections per second, then we get 100% CPU usage on the access point. So essentially, it only supports 8 connection attempts per second, which is very low. And this essentially forms a denial of service attack against WPA3. Now, if you use a smaller elliptic curve, but still one that is insecure, the situation gets a bit better. In that case, if you make around 60 to 70 connection attempts, only then the CPU is saturated, but still it's not an ideal situation. And this also highlights, in my opinion, the biggest problem in WPA3, which is either you have an implementation of this algorithm which immediately returns the point P, but in that case you're vulnerable to timing leaks because you don't always execute 40 iterations, or you decide to always implement these 40 iterations, but then you might be vulnerable to a denial of service attack. So especially if you have a resource-constrained device, there's no optimal choice. Either you don't implement these devices and you're vulnerable to the timing attacks, or you do implement them and then the computations are expensive and yeah, you might be vulnerable to a DOS. One other thing I want to mention is downgrade attacks, because as we all can imagine, and as we all see right now, it will take a time for WPA3 to be implemented in practice. So we need some way that a network can support both WPA2 and 3 at the same time. And how the Wi-Fi Alliance decided to tackle this issue is that, okay, an access point can simply set up a network, so one single SSID name, and this SSID will support both W2 and 3 using the same password. Now the question is this secure to do? Well, against one attack scenario, this actually provides some security, because let's say we have a client on an access point that both already support WPA3. If I then would try to do a man-in-the-middle attack against them and try to downgrade these devices into using WPA2, the WPA2 handshake would actually detect this downgrade attack. It would realize, oh no, there's actually a stronger handshake available, and the handshake will be aborted. Which means that this solution provides forward secrecy. Unfortunately, there is a big problem with this though, and this is that even though when we perform this downgrade attack, the WPA2 handshake would be aborted, the partial WPA2 handshake that is executed is enough to perform an old school dictionary attack against WPA2. So if you configure your network to work in WPA3 transition mode, this means that an adversary can still downgrade your clients into using WPA2. The client will eventually abort the handshake, but the adversary will have enough information to still do a dictionary attack. So now you might be wondering, well, okay, this is a problem, but can we actually defend against this? I mean, it seems like a hard thing to do. Unfortunately, there's one solution. It's not 100% perfect, but it makes attacks a lot harder, which the thing that we do there is we let the client remember if a network previously supported WPA3. And if we know that we previously connected to a network using WPA3, then in the future we're not going to fall back into using WPA2. And that would prevent a lot of automated attacks. And this idea is similar to the trust on first usage of SSH, and also to HTTPS with strict transport security. So it's trust on first usage. And the good thing here is that by now the network manager of Linux is in fact implementing this defense. So if you use the latest Linux distribution, then you will have this countermeasure. And the same is true if you use a Pixel 3 smartphone. In that case, it is also implementing this countermeasure where once you connect to a network that supports WPA3, it won't automatically downgrade to WPA2. Okay, so that covers downgrade attack number 1. There are more downgrade attacks. The second downgrade attack is a downgraded attack against a crypto group. Remember that we can execute the Dragonfly handshake using either mod-p groups or elliptic curves. And the question is, how do we negotiate which group we are using? Well, this is done very simply. The client basically proposes a group to be used when it decides to connect, and then the access point either accepts that group or it sends a reject message saying, hey, I don't support this group, use something else. Now it turns out that this reject message is very easy to spoof, and on top of that, after the handshake would complete, there is no way that the protocol verifies that there were no downgrade attacks. So the summary here is that we can force the client or access point into using a specific elliptic curve or a specific mod-p group, and this is again really a design flaw in the handshake. So this is downgrade attack number 2. Does anyone think there will be a third downgrade attack? Of course there will be, but this one is specific to implementations. So the previous 2, they were in my opinion more in the area of design flaws. This is only an implementation specific downgrade attack. And what happens here is that for certain devices, I'm talking here now about client devices, if they connect to a WPA3 only network, in that case, there's no reason for this client to ever downgrade to WPA2. Because when it connected to the network, this network only supported WPA3, so there's zero reason to assume that in the future it will switch back to WPA2, unless you are in an exceptional condition. Unfortunately, it turns out that with the Galaxy S10 and also with the Linux IWD Wi-Fi client, which is a fairly recent open source Wi-Fi client, against these devices, if they previously connected to a WPA3 network, we can simply set up a WPA2 network with the same SSID, and then these implementations will happily connect to the WPA2 network, meaning we can still do all the attacks of WPA2. The good news is that it's now patched on the S10. I think if you have an update, it should be fixed now. I don't know exactly the situation with IWD. But again, this is an implementation-specific attack. It isn't really a flaw in the specification. Now, I'm going to leave some time for question as well, so I'm going to skip part of the disclosure that we followed. The one thing I want to mention here is that the Wi-Fi standard is now being updated to be more secure. In particular, the standard is being updated to prevent some of these downgrade attacks. And on top of that, the standard is now also being updated with a different algorithm to convert the password into this group element P. And this algorithm is a constant time algorithm, meaning there are no more timing leaks and there are no more cache attacks. And this is done both for mod P and elliptic curve groups. So in both these cases, a different algorithm is being proposed so that there are no more timing leaks. On top of that, previously it was unclear which elliptic curves and mod P groups you were allowed to use as an implementer. They now also have more clear guidelines on which groups are secure and which are weak. So this might actually lead to WPA3 or 3.1. It's unclear how this will be handled in practice. But I do want to warn about the risk of possible downgrade attacks here. So they are working on these updates to the protocol, but the risk here is that maybe implementations can still be downgraded to the first version of WPA3. The last thing I want to mention is that we saw a lot of attacks against WPA3 here, but even with its flaws, right now WPA3 is still better than WPA2. So if your devices support WPA3, you should still start using it. Because with attacks we discussed, we can do dictionary on brute force attacks after performing these rather tedious timing on cache attacks. While with WPA2, you simply need to passively capture the handshake and then you can do all the attacks. But with WPA3, this is still a lot harder to do. And on top of that, because we were early in finding these flaws, my expectation is that a lot of vendors will patch these flaws, and that as an adversary it won't make sense to invest a lot of time to make these attacks practical. So my hunch is that these dictionary on brute force attacks, hopefully they won't be applicable in real life. So that leads to my conclusion. Essentially, the first version of WPA3 was vulnerable to side channel attacks. The countermeasures are quite costly and tedious to implement. That's why the standard is now being updated. But even with this, remember that WPA3 is, at least for now, still better than WPA2. So if you have the chance, do switch to WPA3. So with that, thank you for your attention. Are there any questions?
Yeah. Questions? No? I think there's one question. Sorry. What?
Hi, thank you for the talk. I'm here. So you're saying the standard is being updated, but you mentioned that the manufacturers don't respect the standard in the implementation. How do you think that will work in the future?
So most vendors, I mean, they do have to respect the standard in order to be compliant. So right now, I think most vendors are following the standard as best as they can, actually. I think the main, so I don't know how vendors will react. I do believe that most vendors will implement these defenses, and the reason why is because the algorithm that is used there is much more efficient. So here we had this defense where you had to execute a variable amount of iterations, and if you implement the defense, you have to perform 40 iterations. This update to the standard is actually much more efficient, meaning there's a good motivation for vendors to switch to it because it means it uses less resources, it would save on your battery life, and so on.
Was that the question? Another question, sir? No. Okay, cool. Thank you, everybody.
Thank you.
Lunch is served.